Sir, whether my voice is audible?
Yes, ma'am, you can proceed.
Okay, sir. Okay. Good evening, one and all. Now we will begin with our second session on battery management system, AI for SOC, SOH, and performance optimization, delivered by our esteemed speaker, Mr. Suraj SD. Before we proceed with the session, let us have a brief introduction of our expert, that is Mr. Suraj SD. Now, Mr. Suraj SD is a seasoned automotive and electric mobility professional, entrepreneur, and educator with extensive hands-on experience in EV, powertrain research and development. He is the founder and CEO of Decibels Lab, where he leads initiatives focused on electric vehicles, autonomous systems, and automotive electronics, while also serving as program director for its e-learning platform dedicated to industry-oriented skill development. With deep expertise in electric powertrain subsystems, including traction, batteries, motors, controls, thermal management, HVAC systems, drive cycles, and cell characterization, he has worked closely with teams of engineers on advanced EV technologies. Mr. Suraj holds a bachelor's degree in mechanical engineering and has a rich global industry exposure through projects with leading automotive OEMs such as Mercedes-Benz, Fiat Chrysler, GM, and Fisher Dynamics in India and USA. His professional journey spans roles in design engineering, automotive plastics, seating systems, and consulting, and he is a certified in hybrid and electric vehicle technologies and high voltage safety. Passionate about building a sustainable EV ecosystem, he actively bridges industry needs and engineering education through innovation, entrepreneurship, and skill-based learning. So now, with these words, I request Suraj sir to start with his session. Thank you. Thank you, sir.
Thank you a lot, madam, uh, for the introduction. And thanks a lot, Udumkar sir, for inviting for the session. And it has been an engagement with DKT for about several years. I think it's more than 7 years almost, setting up the lab and being working together on various activities of engagement. It's really a good opportunity for us to explore through this faculty development program. The topic that is given to me today is on the AI for BMS. It's a very fancy word and fancy thing. We hear AI to be used in every single other things in the day-to-day activities, and we expect it to perform the tasks that are more complex in nature, maybe such are highly data-driven in nature. To Before we start the topic, I would like to just do some basic level of understanding with the participants. There are a lot of people, um, maybe many of you have gained more experience than what I may have today. Also would have been working in the battery industry or BMS activities or any of those areas in place. So maybe out of you, some of you may be just in the session, not listening to it, or some of you may be actively listening to the session. And that's what usually happens in online classes or lectures. Would like to maybe hear from 2 or 3 participants in the session. What would you like to really gain through maybe that 1.5 hour of interactions that we're gonna do, so that I try to keep my content just focused to those topics, and it becomes very relevant with our interactions in place. I would like to hear from any of participants, at least 3 to 5 people, to set a benchmark that what is your expectations from 1.5 hour of interactions. Over to anyone out of 74 to give your inputs, please.
Sir, we want SOC estimation with the help of AI.
Okay. I'm just noting it down so that we can have the interactions. Okay. Anyone else? I'm unable to hear anything. Is there a problem from my side? I assume so, because I believe rest of the people are able to hear. Okay, so we hear that somebody would like to get an idea of SOC estimation with AI. Anybody else? What is your intention to be a part of this FDP, or anything that you would like to take away? Maybe we'll not go ahead until we really like to get some input from you, because that sets the importance for me also to interact. Battery health monitoring and cell balancing via AI. Interesting. Okay.
Uh, Good evening, sir. If there are any real-time examples, how the performance is improved or efficiency is improved by using SOH and SOH and SOC. So,
Okay. Case studies, very interesting, which improve the estimation with the help of AI. Okay. I'll try to see if I can pull in something by the second session after the break. Anybody else would like to make a point that I can note? How to AI helps to optimize battery performance. Okay. How AI can help. Okay. AI can help to optimize battery performance. Sure. Anybody else?
So some challenges what we are facing about that.
Okay. Battery monitoring and cell balancing. So, yeah. Challenges we are facing. Okay, so great. I think we have some good inputs. Anybody else would like to jump in and add a topic that it may seems relevant for you?
Sir, good evening, sir.
Good evening.
Hello. Yeah, thank you. Sir, yesterday that sir had explored battery management system.
Mhm.
So today I had a question also. For managing the batteries, those 5 modules are implemented, like uh, SOC and all.
Mm-hmm. Mm-hmm. I'm sorry,
These are
Sushil.
implemented.
I was not there yesterday, maybe in the interactive sessions.
No,
I'm not sure.
SOC, SOH, and RUL and thermal runaway detection, and one more
Okay.
optimization.
Okay.
So
Okay.
these 5 modules are implemented for battery management system.
Mhm.
That is my simple question.
All right. Okay.
Thank you, sir.
So,
Thank you.
sure. Thank you. So let's start with your
Thank you.
question. Thanks for asking all the questions and also sharing your inputs to learn about today's session. Yeah. So if you take any BMS, we have two different things in the BMS. At the software level, we call as a base software, and we call something else as application software. most of you might have been very familiar with the terminology that we call it as. So the base software consists of device drivers, typically any drivers that talks to you about AFE, that is called as analog front end. The analog front end is a hardware component in any BMS today, which functions is to measure cell voltage, measure cell temperature, also in some cases measure current, and then do balancing, right? Also do some level of communication with the microcontroller or to another AFE. So I'm not sure how everyone is familiar how BMS works at the hardware level, but to do anything as estimation, we call it as SOC, SOH, RUL, call it as remaining useful life, anything, we call it as SOX, state of power, state of energy, many other things that comes as a part of it. But all of that is based on what your BMS is actually measuring, right? The BMS only measures these three parameters. It measures voltage of the cell, it measures few temperature, it measures the current of the battery pack. So to do this, we have hardware components, which we call it as AFE, that is called as analog front end. Then we have MCU, that is microcontroller. We have real-time clock on the hardware. We also have something called watchdog, which takes care of the functionality to be ensured if there is any failures and stuff like that. We have communication interfaces where the BMS sends the data to somebody else via CAN and things like that. So it's basically the hardware. We call it as the BMS. Maybe just because AI is a superficial topic that we can talk, but I just want to lay a foundation to make anybody relevant about what is in the BMS. Then we jump in slowly over the number of topics to discuss. So just give me a second if I can pull in a video that we have on our channel, and then okay, maybe I'm not sure if this is the whole thing. Okay, how many of you maybe participating in the session have a hands-on experience with BMS or ever worked along with cells and BMS or anything of that sort? Anyone? You're just trying to find this video I can just showcase. Yeah. So I'll share my screen. I'll keep it maybe slightly slow also, just to make sure the emphasis is about learning something maybe a little, but really getting it everything that is possible. Out the battery management system hardware. So actually what's there inside BMS packs, maybe on the BMS. So if you see, it's always I see importance about the foundation to what we take it ahead. This is an hardware of the BMS. If everybody is able to look and get a visualization. So you have an option here to read the data from the cell voltages. That's just the connector which goes to the BMS, sorry, the battery pack. Then you have component called AFE, which is called analog front end, which is connected, which all the cells are connected primarily through, because you can't just put a lot of voltage dividers and then read voltages. Your accuracies are challenging to do that. So there is a specially designed IC, which basically does all of this voltage measurement, temperature measurement, also sometimes the current measurement as well. It can also do balancing. As I said, it can do communications and stuff like that.
So first, this is the place where you have all the voltage signals that is coming from your lithium-ion battery pack. So this BMS are designed to handle only specific number of cells. So some are handled to design only 13, some are handled to design 14. And maybe here you can see that, there is the specific number of cells that this can handle. This should be able to handle about the 15 number of cells. So you can see here that there are a set of MOSFETs, which are here on the first line. And then you have a set of RC filters. So RC filters are the one that being used when the voltage is been coming to the lithium-ion, from the lithium-ion cells to the BMS. Basically, they come via these RC filters. They help you in filtering certain signals, which are the voltage signals. Then from these RC filters, the signal will go to the component called AFE. The AFE is basically an analog front end, which kind of takes care of handling your voltage measurement, and it also kind of handles few other activities as well. So now you understood that the voltage is coming from these components, and then it is going to the filters, and then you go to the AFE for the voltage measurement. Then you also have the microcontroller that is here, right? So these microcontrollers are the one that typically kind of does your computational activities, maybe like the SOC estimation, SOH estimation, cycle counting. Typically that is happening inside this microcontroller. And different suppliers have different microcontrollers. So you have NXP.
Sorry, sir. Is it
the sharing is not available? You have not shared the screen?
Oh, I'm sorry. Sometimes I think
Huh.
it is being stopped to share. That's some problem
Yes,
with.
just check.
Yeah, just let me know. So if it stops to share, always just remind me about
yes.
it.
Okay. Now it's visible, sir.
Okay.
So you can see here that there are a set of MOSFETs, which are here on the first line, and then you have a set of RC filters. So RC filters are the one that been used when the voltage is been coming to the lithium-ion, from the lithium-ion cells to the BMS. Basically, they come via these RC filters. They help you in filtering certain signals, which are the voltage signals. Then from these RC filters, the signal will go to the component called AFE. The AFE is basically an analog front end, which kind of takes care of handling your voltage measurement, and it also kind of handles few other activities as well. So now you understood that the voltage is coming from these components, and then it is going to the filters, and then you go to the AFE for the voltage measurement. Then you also have the microcontroller that is here, right? So these microcontrollers are the one that typically kind of does your computational activities, maybe like the SOC estimation, SOH estimation, cycle counting. Typically that is happening inside this microcontroller, and different suppliers have different microcontrollers. So you have NXP, you have Infineon, TI, and many of them are there who supply you these ICs and also these ICs as well. And then you can see some sort of resistors here. The resistors which are being present for the each cells. So, and these are basically your balancing resistors. They help you in balancing. And then you see these MOSFETs, these are the one which controls which cells to get balanced. If you want the cell 1 to get balanced, cell 1 to get balanced, cell 15 to get balanced. Basically, this is all done by your set of the MOSFETs which are present here, which are kind of very closely the three-legged components that are in the beginning of these lines. And then you have your MOSFETs, which are here, which is a slightly larger MOSFETs compared to these ones because they handle larger current. So these MOSFETs are the ones which basically handle your charging cutoff or a discharging cutoff as well. Let's say you want to limit your discharging cutoff to 50 amps, right? So these MOSFETs are in certain configuration, and they handle suddenly the part of your charging circuit and certainly the part of your discharging circuit as well. And then you see some small of these components. These are your, I would call it as the The shunt resistors, they help you in measuring the current when it flows out of or inside the circuit. That is what helps you in Coulomb counting as well. And then you have some LDOs, they take care of your voltage dropping from specific voltage to a lower voltage, and they help you in the running the power supply to the microcontroller or running the power supply to your AFE as well. So what else is there? So you have sometimes the driver circuits that's been driving the set of MOSFETs, because you can't directly drive your MOSFETs from your microcontrollers straight away. So you have some drivers as well, and some of your other RC components or resistors and
Right. So I think on that perspective, if we are able to build a basic idea, right? So the BMS is able to measure voltage, temperature, and current. And then you can read the data in the AFE, and from the AFE, the data goes to the microcontroller. And the microcontroller is the component which basically does all your calculations. Okay. Now, my first question to talk about AI. Maybe many of you have really been dealing with microcontrollers. Have you ever come across AI getting implemented, or somebody tried to implement AI on microcontrollers? Okay, so, and I would like to get some answers from anyone that have you ever dealt implementing AI in a microcontroller?
Maybe on Raspberry Pi.
Okay. That will be a processor, if I understand, right? The AI, the Raspberry Pi will be a processor than a controller, like a microcontroller. Anybody try to run AI on a microcontroller? Okay. Right. So that's the first important thing, we need to realize that AI is definitely very fancy, but when you see the video, the intention of me showing the video is that what you have on the hardware, like we can call it as edge level computing, the BMS has very, very limited space, very limited cost, that it largely has just the microcontroller. And the microcontroller hardly would have a flash memory of about 500 kilobits, and which is possibly about half an MB of storage that you could run through, flashing all of your base software, application software, all of these things. And then there are critical, important activities that the BMS has to do, um, where where if you take an example, measuring voltage, check if the battery voltage goes high. The priority for the BMS is to make sure the battery is safe. That is the fundamental functionality of the BMS, right? So the next functionality of the BMS is about estimation. And the third priority for the BMS is to estimate everything accurately and enhance the life or optimize the life of the battery, right? But the primary thing is that, what can you do if you cannot make your battery safe, right? The primary functionality of the battery BMS is to ensure that the batteries are safe. And then we talk about estimation, and then we talk about optimization. So primarily, when you take a BMS, your hardware at the edge is very tiny, very small. You don't have like a CPU or like a processor sitting inside the BMS. So somebody need to realize that the implementing AI, like a edge AI, is not something very straightforward. on a BMS. So nowadays there are components, there are companies which are developing microcontrollers. They may be already available microcontrollers which are multi-core in nature, but the cost of them is expensive because when you come to automotive, just then there's a research, it is a different thing. But when you want to make a BMS and then deploy the BMS in the product, there is a price point. Maybe it is 3,000, 4,000, 5,000 rupees. It is really challenging to think about putting a processor on the BMS, right? So then what is the topic that we talk about AI in BMS, right? So it is a kind of a strange thing to start with. So the idea behind AI now, if I just put that, a line of statement that, hey, it's not just straightforward to implement AI in the BMS, then how do you think AI can really help in doing anything with BMS? Then what is the intention of all of this AI inside the BMS? If your hardware, let's say you don't have a computer, for example, right? Can you just take a very old computer and run an AI on top of it? No, it will definitely struggle, right? It will not have computational power and energy that it can utilize to run AI models, right? Then what's the point of we talking about AI? How AI is feasible to be implemented for BMS? Any answers from anyone? Anyone has an idea that, how does it make sense to talk about AI or implementation of AI for a practical battery management system? Any inputs from anyone? So how it makes sense to really use AI in BMS if your hardware itself is not capable, or if the hardware is limited by the cost? Yeah. So taking ahead the topic that yes, this is something as a bottleneck to use AI, uh, you know, at the BMS level, at the hardware of the BMS. As I said, nowadays there are companies who are developing microcontrollers with a higher processing capabilities, also multiple cores, because uh, if you have single core in the processor in the controller, you have different priorities that microcontroller has to run, because you have protection logics, you have all of those logics which are more important in the BMS to run. So to run AI and stuff like that, you may have to have multiple cores, so you can just tell one of the core to do some edge level AI and stuff like that. And also you would need to develop highly light models, like not a very computationally intensive models, and data-driven models, which are very more simplified in nature. If you really have to implement AI on the edge, that edge means on the BMS, okay? Then what is the point in going next? So what people do today, somebody asked me, hey, what is a case study? Okay, before that, the last question was, what are the four things that exist in the BMS? So I showed you the hardware. That is what the hardware is, the BMS. Then you have the software, that is your base software. Then you have an application software. The base software has all of your device drivers and base level setups to communicate the hardware with the application layer. And in the application layer, you have all of your algorithms, BMS, protection logics, SOC, SOH, cell balancing, anything else that comes as a whole application software, protection logics, uh, the software level safety to ensure the hardware will not get into a trouble. We can call it as fail-safe management systems and all of that. So they're all existed in the part of it. And then connecting to the AI as the functionality. So it is really hard to put AI on the edge. So what people do, as a case study, somebody was asking me that companies like Ether, I have heard that they have the IoT module in the vehicle. So the BMS does all of this data collection. It does SOC estimation, SOH estimation, all of that on the board with the hardware algorithms that can run on the hardware. And then the data of these information is sent to the cloud via the IoT modules. And in the cloud, you have the feasibility of computation. So you can get all of this data to the cloud, and then you run the AI models that you want to develop in the cloud, right? So, and then for each maybe individual battery, you have an identity of asset as a digital asset. The data in the hardware of the BMS and on the in vehicle, its temperature, the voltages, current, all of that is sent to the cloud, and then user profile, how the person drives the vehicle, when he charges it, how much he drives the distance every day, how much he stops the vehicle, what is the time, what is the SOC at which the vehicle is parked. Everything is captured, okay? And then all of this data is now sent to the cloud. In the cloud, you have enormous amount of power that you want to run the algorithms, right? So you can optimize and run your algorithms in the cloud. So that is typically the way of architecture that exists today, uh, where we can use AI and then do some level of computations. That's the feasibility of implementing AI in the BMS. I hope that brought some level of understanding for anyone to know where we use AI, um, how we use AI, how we can use AI for BMS. So that's the topic of introduction. If I say how AI makes sense, it makes sense only when you have cloud, you have data that is collected in the cloud over the number of years and years. So the next thing, um, how much data are we gathering, right? To make sense of AI, because AI need to be taught, and maybe they statistically or with the neural networks and stuff like that, right? So for all of that, you need data. So what is the data that you're trying to measure, right? So the only data that your BMS gives you is the voltages, temperature, current, the rest time, the charging time, the usage pattern of the battery. That means how many hours is your vehicle standing at what SOC, at what temperature, right? Because the battery has a degradation characteristics, because it's a chemistry and a lot more complex to realize over a simple equation. It's highly a nonlinear system. If you are, let's say, in Delhi and you have a bike or a car, um, you travel average about 50 to 80 kilometers in a day. Let's say it's a bike, right? That means you have to charge your vehicle every day, right? You go to your office, leave your home about 8 o'clock in the morning. You reach to your office about 10 o'clock, because you drive 2 hours to reach 35 kilometers, 40 kilometers every day. So that means your vehicle is fully charged when you leave your office. So you leave your home. Imagine your battery is 100% at 8 a.m. And then you drive your vehicle, it may become 50%. You stop your vehicle for about 9 hours because 9 hours is your working hours. Then you take your vehicle from your office about 7 p.m. The battery was stored at 50% SOC every working day from 10 a.m. to about 7 p.m. Then you leave your office about 7 p.m. and then you reach your home about 9 p.m. Then you keep your vehicle for charging, right? The battery may take 5 hours to charge. Yeah. Then 9 p.m. you have kept your charging. So the charging is done by 2 p.m. So 2 a.m. at night. And then the battery is sitting idle at 2 a.m. until morning, maybe 8 a.m., right? So it is not doing anything, but it is sitting at 100% SOC from 2 a.m., 3, 4, 5, 6, 7, 8, about 6 hours. Yeah. So if you see, let's say you're living in Delhi, and then what is the temperature of Delhi, right? At the coldest days, the temperature can go up to, let's say, 0, I think. I'm not sure. Close to 0, I believe it can go. And in the daytime, maybe the temperature can go at a hot day about 40, 45 degrees Celsius. Yeah. Imagine the temperature at which your battery is operating, right? And the same thing if you're in Pune, if you're in Rajasthan, if you're in somewhere else, yeah. If you're in north, where there are a lot of hill regions and terrains and things like that, right? So that means the battery that has been sold by a company is now sitting across the country at different temperatures and different patterns. Maybe somebody else, if you take the same bike, other person is using, he only uses 20 kilometers in a day. So he don't need to charge every day, or that gentleman may charge every day. So one customer charges the battery uh, in the morning to 100%. By the time he comes back, it is like 20%. Then he charges the battery over the night, it becomes 100%. It sits there. So other person maybe only uses 20% in a day, then he don't charge for 3 days. Maybe there's one gentleman who charges every day, even if you use 20%, right? So there are a variety of patterns at which the battery is being charged and kept idle, being used, all of that. Then that same customer drive in different way. One guy may drive very aggressively. That means the current that is drawn from the battery is not same, correct? And some person may have terrain, like if you live in mountain areas, you have a lot of terrains, so that current drawn is very high. Somebody may put a lot of load. They may carrying some equipments every day to sell something of that sort. So the current utilization pattern of the battery is different, and so the battery behavior is slightly different, right, during the usage. So when you study all of these things, right, there are million of permutations and combinations. If you have sold 1 lakh vehicles, there are 1 lakh patterns at which the vehicle has been used. So then how do you know how your battery performs for all of these conditions? Because you really cannot replicate everything in the lab. You cannot really replicate 1 lakh patterns of usage in the lab, right? So now what you can do, if you have devices data that is like data of your vehicle that you have sold to your customer sitting on your cloud, and you can use your intelligence with the help of AI, machine learnings and stuff like that. Yeah. So what can you do with the help of the data? Maybe I will throw some light with some sort of presentation I have. Yeah. So I don't know how many of you have a practical exposure to battery. Inside the cell, we have a lot of material, not a topic that I've my assigned today, but yeah, somebody, if they have not seen the cell inside, so the cell has anode, cathode, active material, current collectors, separators, electrolyte, tabs, terminals, a lot of these things, yeah. So whatever you're reading is a voltage and temperature and current is internally the chemistry. It's internally the reactions that is happening. It's internally the material that is, where the ion exchange is happening, and that is leading to an electron exchange in the outside environment, right? So we are just reading the electrical characteristics of the battery, but trying to know what we call it as SOH, right? SO, state of health, and what is called SOC, a state of charge, that how much ion is left in the cathode, left to be moved to an anode, or from the anode to a cathode. We are trying to do all of these calculations, which is actually the back end is chemistry, right? There is millions and trillions of things that are happening as reactions, but you're trying to superficially define all of this through three parameters: voltage, temperature, and current. So you're trying to use this data as your information to go back and understand, oh, what is my health of the battery? So it's like you running, maybe you go to a doctor and you want to test your health. You tell the doctor, our doctor tells you that run on a treadmill for about 5 minutes, and he can measure your heart rate, he can measure your blood, whatever the things, stuff like that. And then maybe he can tell you how good is your body, right? And but internally it's an organs and a lot of things that existed inside, but he's just trying to measure some data on top of it. He can tell you, okay, how good you are, but truly you don't know how is your cell, how is your membranes inside your heart, or whatever those things are, how is your genes are, what you carried out from your parents, and what issues, health considerations and stuff like that. The same thing in the battery too. So you're trying to just measure voltage, temperature, and current. And when you're measuring temperature, you're just measuring the cell body temperature, right? You're not going inside and measuring the material temperature. You're just measuring the body temperature and assume that, okay, hey, this will be the temperature of the cell, but it is not truly the temperature of the cell. It is just temperature that is at the surface of the cell, right? And then trying to build a model that tells you that based on this data, how my battery health is degrading. And that's the perspective of what we're trying to connect the data and the topics of AI to know what is happening inside the cell as material. Okay. I'm not sure how many of you from chemistry as a background, to know what really happening inside the cell, and that is actually depicted as SOH and things like that. So let's assume an understanding between us today and the simplicity level, then going to complex. I'm not sure, at times the screen sharing gets stopped. I believe you're able to see my screen. Anybody can confirm?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. So let's take an example of state of health. Okay. So what is state of health? It is that comparable value of the capacity of the cell today to the fresh cell. That means when I purchase the cell or a battery, the cell is at, let's say, 10 Ah or 100 cell in my day one or cycle one. I use the cell or a battery over about 2 years. I charge, discharged, all of that. So it has degraded over the number of days. And at 2 years, if I test the same cell or test the same battery, how much capacity I get, right? AH as an ampere. On the day one, it is 100 Ah. On the 2 years later, the capacity would be, let's say, 80 Ah. Okay. Then what is the state of health? It is 80%. That means you lost 20% of the battery capacity because you have used the battery, right? So when you say you lost, so where did it go? Did you take out ions? Did you take out lithium from the cell? No, we did not take lithium from the cell, right? That is inside the cell, but what happened to that cell? What is not able to give you that capacity when on the day one it was able to give you 100 Ah, like your mobile phones. When you buy your mobile phone, it gives you good backup, and after 2 years, it doesn't. So the battery is same. You did not take out any materials inside the cell and just use it for something. So it is inside the cell, but you're not able to get the same outcome that you got in the first day. So if you study it intrinsically, so there is lithium repository that when you create a cell, you put the lithium repository on your cathode side, and then you do a formation cycle that is called as first charge and discharge cycle to form. That is like to give a birth to the cell. Like in the manufacturing plant, you have cathode and anode, and then both of them come together. There is a separator, and then the manufacturing happens, and then you fill in electrolyte, and then the first ever time in the life of the battery or the cell, you charge it. That is called formation cycle. So in the formation cycle, the ion in the cathode side goes to the anode side, and then when you discharge the cell, it comes from anode to cathode. So something is happening inside the cell as ion transfer. So when this is happening, you start to lose something. Basically, your currency is your lithium. So lithium goes from cathode to anode, anode to cathode, cathode to anode, anode to cathode. During this process, the electrons are moving around outside, and that's what you get as the current, right? So if you discharge more current, there are more ions flowing in. If you discharge less current, less ions going through. But where did the ion go? When you say SOH, that is state of health, we define that with two terms usually. State of how much capacity retention it is having and the power retention it is having. The capacity means, I give you an example, 100 Ah you got on the first day of the cell. On the 2 years later, you're getting 80 Ah. So somewhere you lost that 20 Ah. Like you have stored 10 liters of water. After 2 years, 2 liters has gone somewhere, but you don't know where it has gone. But you still close the lid of the lid of your cap. So that's the capacity retention, we call it as. Then we call it as state of power, right? So the cell was able to deliver 10 amps at an instance when it was very new. But today it is not able to give you 10 amps. It is able to give you maybe only 9 amps, 8 amps, because it has built in a lot of internal resistance, or maybe it is not able to deliver you an output. So these two things returns back to a word called state of health. Uh, the ability to do a capacity retention and power retention. And now you want to estimate these two things, how much capacity that is retained inside the cell, how much power it is retained in the cell. Very simple things, right? Very, very simple words to tell. But actually what is inside the cell is the ion. So if you say capacity, it is like currency, right? The lithium ion is in the state of currency. So it is exchanging from cathode to anode, anode to cathode. Somewhere in this process, you lost 20% of lithium. So what happened to that lithium? When I said I lost capacity, I lost lithium inside the cell. So what really happened to that lithium, right? It is lost somewhere in the whole cell. Maybe there is a process of lithium plating. There is a formation of, we call it as dendroids. There is some amount of material being consumed in the process of SEI formation. Uh, so many other things. Okay, so you lost that lithium, and when you keep charging and discharging, charging and discharging, it is not like a reversible, fully reversible reaction. There will be some amount of things lost during the process of charging, during the process of discharging. We call deeper topic as intercalations. So this process is we're trying as an engineers to simplify the chemistry and trying to call it as capacity retention. Okay, but inside the cell, it is about ions being shifted between. Where did you lose those ions? So this characteristics of the cell is inherently depends upon various things. Maybe if I go through a few more slides that we have, and maybe if I just draw two more topics here, that I talk about the inventory of lithium. The second thing is that the power. So I don't know how many are aware about what is there inside the cell. I really recommend, if you're teaching a subject in university or a college, not safe always. Make sure the cell is fully discharged to a very lowest voltage. Have safety masks, maybe wear uh, chemical masks so that you don't inhale gases coming out of the cell. You cut a cell, you open the cell in a safe environment with the right safety tools, because you have lithium, you have also other materials which can form HF. It is highly dangerous. If you consume it, you may get a lung cancer. So be very careful because the electrolytes are highly dangerous in nature, carcinogenic in nature. So just do not let any students to cut a cell and play with the cells, because there can be a chances they get a cancer one day if they don't take precautions properly. Also, in any production plants, the electrolyte is one of the most dangerous element. That is why there is during the electrolyte process, and there is drying process, we call it as, the electrolyte is extracted and then sent to a purification process. So you cut a cell with, if you have these precautions in place, and study what is there inside the cell. So we have copper, we have aluminum, they call current collectors. And then we have binding materials, which binds the active materials to the copper, active materials to the aluminum. All of these things existed. So when you start using the charging and discharge battery, you do a charging process, discharging process. So during this whole process, the copper may get corroded because it may have some impurities. And we may have some of the cracking of the active material. So we may have some other things which comes into a play. We call it as SEI layer. So the surface of the active materials being covered by a thicker and thicker SEI layer, so the interpolation doesn't happen. So all of these things leads to something called internal resistance. That means the cell's internal resistance will increase. And that means the cell is no more able to deliver an output power, and it is no more able to deliver a capacity that you designed it for in the beginning days. So these things lead to something called SOH, as state of health. And going through to dig a little deeper why AI is meaningful to be used, that now you know what is happening here inside the cell. It is chemistry. This chemistry is subjected to variety of inputs. Let's say I talk to you as an example that if somebody in Delhi is using his vehicle, the temperature can go so low. On the daytime, the temperature can go so high. The battery is stored at morning because it is charged to 100%. It is sitting at 100% from 2 a.m. in the morning up to 8 a.m. in the morning. 6 hours it is sitting at very high SOC. We call this term as degradation. So there are two types of degradation. One is called calendric degradation. Other one is called cyclic degradation. So calendric degradation is like you don't do anything with the battery. You just keep the battery, it degrades because it's a material, right? And next thing is that it degrades when you're operating it, when you're charging or when you're discharging. That means when you're driving the vehicle or during the process of charging, there is degradation. Even when you park the car, park the bike, because it is standstill, it is called calendric aging. Okay. So the calendric aging or the cyclic aging is highly dependent upon many things. If you take calendric aging, it depends upon what SOC is your vehicle stored at. It also depends upon what temperature the battery was stored at what SOC, right? If you store the battery at very high SOC, at higher temperature, degradation is much faster. If you store the battery at very high SOC at a very low temperature, the degradation is faster. I'm just giving you an example. It may be true for a cell, it may not be true for the cell, just this, the relevance is in place. So imagine what AI can do. Maybe if anybody can give me some hints about what AI can do in understanding the calendar gauging and what solutions can this suggest? Any inputs from anyone? Any inputs from anyone?
Oh,
All right. So I can give you a case study. This was one of the practical examples what we were trying to think about. There's a company, they make swappable batteries. So they have about 35,000 batteries in the field. And these batteries are swappable. Okay. These people, like two-wheeler companies, use this, like delivery companies or delivery agents. They use this batteries. So what do? They do the deliveries from morning to evening, at night also sometimes. Before they go home, they keep the battery for charging in the big charging stations. So I said you like it takes 5 hours, 4 hours to charge, right? So at night, maybe about night 9 o'clock, they keep it for charging at 10 o'clock. So moment you keep it for charging, the charging used to happen. So the battery gets charged till 100% by 2 a.m. And then the battery was sitting at that 100% SOC from 2 a.m. to morning, maybe 7 or 8 a.m. So then the person comes back, takes the battery, puts it in the bike, and then goes around the city for delivering things. So the whole cycle repeats every day. The same thing, because they also had batteries in Bangalore, they have in Mumbai, they have in Chennai, different locations. So what they observed at the first level is that maybe in some cities the batteries have degraded much faster compared to something in Bangalore. Let's say take an example of like Delhi. The Delhi operates at most extreme temperatures. So maybe at 45 degrees Celsius, at night it may go to like 0 or even 5, 4 degrees Celsius. Cities like Bangalore, we don't touch that low. Maybe we touch something like 20, 18 degrees Celsius. And then at a max, we reach 35 degrees Celsius. So when they observe the data that they had, and what they're able to conclude is that the batteries are getting charged to 100%, sitting there at idle conditions from 2 a.m. in the morning till 7 a.m. in the morning. And during this process, the calendric aging is very high because you stored the battery at higher SOC. And also the temperature at which you stored, you cannot control because that is environment. There is no control over about what you can do in environment, right? So what they did is that they when you connect when the person comes back and puts the battery for charging, the battery doesn't get charged. It just stays there. Or if it is too low, maybe if it is like 5% SOC or 2% SOC or 10% SOC, they charge the battery till about 30% SOC, only 30%, maybe in 1 hour, 1.5 hours. And then they just let that battery be there at that SOC. Then till about, let's say, 3 a.m. or 4 a.m. in the morning, it is connected but not charging. And then they charge the batteries with automatically their algorithms from 4 a.m. till maybe about 6:30, 7 a.m. So what they did, they avoided the battery to sit at higher SOC, right? From let's say uh, uh, 2 a.m. in the morning to 7 a.m. in the morning. What they did, if the battery SOC is too low, they can charge the battery till about 30-40%. It is a safe SOC to store where the battery life doesn't get degraded too much. So then they did that in 2-3 hours after the charging, and then they let the rest of the battery, rather than resting from 2 a.m. to 7 a.m., they would rest it from, let's say, 11 a.m. or 11 p.m. or 12 p.m. to morning 4 a.m. So they changed the way that the battery was being charged. With that, they were able to achieve lower degradation. That means the batteries were not degrading much as compared it was before, right? So how could they were able to do it? Because they were able to collect the data of the BMS over the cloud, and they were able to use certain, fundamentally the AI, and later on maybe just a fundamental machine learning. And then now they were able to improvise these things, right? So imagine this get increased over the number of days. 35,000 is a very small number. Maybe it becomes like 2 lakh, 3 lakh, 4 lakh, 5 lakh number of vehicles. Now you want to control each battery, right? So you can set some data points, train the models, and deploy them, right? And then with this data and these models are running in the backend, each battery has an identity, and the data from that battery is badged in the cloud with an ID. And then the algorithm try to refine how this battery is being charged and discharged. And it tries to find an optimal model or an optimal window at which it can be charged, it can be discharged, right? So with this way, you are able to enhance a life of the battery and then make it more feasible uh, uh, to get the best cost benefits. If you see another model, right? So if you integrate the grid along with this, so you want to also make sure you don't, if you charge 35,000 batteries at the same time, each of them, let's say they consume about 20 amps of current, right? And 48 volts. That's about nearly 1 kilowatt. Yeah, it's about a 1 kilowatt. So it is 35,000 kilowatts at, at an instance, right? And imagine if the battery is about 2 kilowatt, average about you have 35,000 into 2, that's about 70,000 kilowatt every day that you consume. That means it is 70,000 multiplied by 15 rupees, that is per unit electricity fees, right? So that is a lot of money. So it's about 75,000, it's about 10 lakhs electricity bill the company is paying every day. Imagine if you integrate this with grid and you have an intelligence to say at what time of the day the grid costs are lower, and maybe rather than it is 15 rupees per unit, it is possibly like 12 rupees per unit, maybe when it is in uh, the, the night time. There is no less load condition. So you can integrate this and also save a lot of money when the charging can happen. You can increase the life of the battery by doing what you can do with the optimization of degradation over calendar life. So these are some case studies that are feasible, that are possible to be done, so that you can use the data that lies on the layer of BMS and cannot do much at the BMS as an edge, but you can push this data over and do a lot of computational activities and then bring it back to see what you can optimize over it, right? One of the case study. The other case study can be maybe any questions from anyone till now about the discussions we have done on the case study.
Yes, Sarji.
Yes, sir.
I want to ask question about the nowadays the electric bike like Ola facing such problem like a battery degradation problem and firing of batteries during summer season. So what are the basic components which are responsible for this bad impact of battery heating and battery fires?
Okay. So it can be a topic that is away from this, for a matter of fact. That itself is a very, broad and a complex topic. I would not say take a brand as a company name and I would say, hey, they have done this wrong. and that's why this is happening. I do not want to. I don't say I have done an analysis of 50 of battery failures, 50 of battery fires, and I have a report to tell. This is the reason. It's very easy as an individual to comment, but for sure, as a company, a lot of engineering time would have happened in the backend. But there may be some situations of something is not going fully correct and would have been some of the failures that we see. Many other companies also have seen some of similar failures also. But I do not truly have a data to classify why there is failures that are truly happening. There are hundreds and thousands of reasons why something can go wrong at a system level. Because there are such non-linearities in the components you're trying to use. To get everything right is an highly and hard thing. Even though you put 5 sigma, 6 sigma quality controls, you still have that 99.96%. That's still that 0.35% has some possibilities of something getting wrong. So I would not say I can comment too much on that topic of failures in the market. Maybe I try to see if I can speak only about today's topic.
Okay, sir. Thank you.
Thank you. Anybody else have any questions? Okay, so I can give you another example as a case study because it is more relatable and understandable for everyone. In the BMS, we have something called operating window of the battery. Okay, so what is mean of operating window? That the battery operates between the under voltage to over voltage condition. So within this window, you achieve a capacity. You achieve the capacity with respect to temperature, with respect to the C rate, the charging and discharging current, the C rate means. So now, when the battery is degraded over the number of days, the performance windows start to change. That means uh, you had manufactured the battery and then shipped the battery to a customer maybe in 2022. Customer has used the battery over the number of days in his own way because of weather conditions and all of that. So when you send the battery or sold the vehicle, you have a software algorithm that is sitting inside the BMS, right? But the problem is that I said this is a nonlinear system. The degradation happens not like in a straight pattern. If you have the degradation happening in a very linear fashion, you can write an equation. You can write an differential equations and things like that to define the curve fitting. But the problem in battery is that it degrades non-linearly. It degrades with so many input parameters. So it is not just a simple straight A, B, C, D, E, F, G, H, or it is not like second degree, third degree partial differential equations you can write and then say, hey, this is how my line is going to fall. It's highly impossible to do that. So the degradation happens non-linearly. So when it happens non-linearly, you don't have the way to write an equation for that, right? So what you rely upon, the data that is coming from the BMS sitting on the cloud with respect to each vehicle, and the way the battery is degrading, you try to optimize the window of battery operation. So that means you're setting your current limits, you're setting your voltage limits, you're setting your DOD of operation, a lot of these things based on how user has used the vehicle. So to do that, first of all, we need to have a model of degradation, which tells you what is good to be used as, and then you take the collect data from each vehicle and send it to cloud, and then you make this data to be used with the models, and then say, hey, this customer is using the vehicle in this way. If I update something of this way, it is okay. And it will enhance the life of the battery. It will make the performance of the vehicle stay same. All of these things. So these are the ways how companies are trying to use AI to leverage technology so that they can enhance life of the battery. And by doing that, they find a way to avoid warranty issues and save maybe millions of money to because if you keep replacing the battery and it just keep failing quite soon, um, it costs them money, right? Every time you give the vehicle back to service and then they replace the battery, it costs a lot of money for the company, right? So rather than that, they use technology like AI to do some amount of learning. And at times, they cannot do everything in the lab, right? They cannot simulate millions of vehicles in the lab. Rather than that, they they use the data of the customer to do learning, to do improvements everyday basis, and then deploy the data over the cloud uh, through something called FOTA. They call it as firmware update over the air. And you may buy the vehicle on the day one with some information inside the BMS. But after 2 years, because they would have updated the software in the cloud, like in your mobile, you have update option. The same way, unknowingly, when you buy the vehicle, they would have take a signature from you that they can change parameters over the cloud. And yes, it is happening today, and they're able to manage it through the firmware flashing, through the IoT and things like that. So that's the broad idea of maybe. I know I cannot maybe say how I can write an AI algorithm. I come from a perspective of architecting ideation to develop or design solutions. So maybe one of my engineers would definitely know how they could write an algorithm with Pythons and stuff like that. So then what somebody need to know about if they want to do something in this area, what competency is required, right? So a lot of interesting somebody can learn. And this is one of our engagement that we did with DKT very, very long back, providing certain equipments and hardware to study. So the first thing, if somebody want to work in the areas of batteries, then starting in AI and AI as a word, I would suggest the universities to have a laboratory, uh, facilities to know how battery behaves. Okay, because you need data, you need intelligence of information to actually do a lot of stuffs in batteries. Yeah. So we at Decibels, we have a state-of-art facility. This is our lab that exists in Bangalore. We have done this in partnership with Christ University in Bangalore. So we have the full-fledged labs. You can see this, there are thermal chambers. We can test the batteries at different temperatures, -10, -20 to +80. So I can simulate any environmental conditions. May not be Antarctica or something like that, or Russia. So mostly of our Indian and Asia continent conditions, I can replicate. I can keep the battery inside my chamber. I can charge, I can discharge, I can do tests and things like that. That will help me in collecting data. So that is very important. You need to know how the cell behaves, right? You study the cell. We also have data that we have collected over 1,000 cycles, 2,000 cycles. So we also sell the data to many customers, many OEMs and industries who want to go in depth in developing these models. And we have cyclers. We call them as cyclers. They just charge and discharge the battery or cell. You can test the battery also. You can keep the batteries inside and then test it. You can do EIS, electroimpedance spectroscopy, a lot of these things. So you need a lot of lab facilities to first know how battery behave. And at Decibels, we do support many universities in setting up these labs to know how to study. So it is not just an equipment, anybody can buy and sell the equipment, but it is having a very in-depth knowledge about how to work with batteries and what you can do as a research areas of topic than just buying an equipment and having 4 or 5 experiments. So we also set up labs which can help universities in carrying out research. And I think this is one of the way better lab than some of the industries also that exists today at Christ. And we wanted to showcase that it is possible to have industry academia collaboration and conduct and carry research. And we use this lab today. Many industries come and test the cells here in our lab. And if you're in Bangalore, we can welcome you to the lab and feel free to visit. So you need some facilities like this where you could actually collect data at a cell or a pack level. So once you have some of these facilities, you also need some infrastructure to work with the BMS, battery management systems, and things like that. At Broadly, we have established about 20 plus labs all across India. So we have some facilities that you can educate your students about how to write algorithms. Or if you yourself want to do a PhD in or do a publications and things like that. So where do you implement finally all of these things? We have developed our own hardware where you can implement the software, you can write your software. We have facilities where you can also write your own algorithms and deploy algorithms, test them. These are test setups that currently that we have as a facility where you can implement and read the data, save the data, collect the data of your battery. If you really want to work further on AI models, you need the data at a fundamental level. The data can be collected by only testing it. That facilities can help you, and then later after you develop algorithms, you can also implement the algorithms in the hardware level too with the help of test facilities. So we are facilitating many universities in doing something of these areas of interest. We have many research projects that we are carrying out with a lot of fundings from in India, also from abroad too. So that's just the broad ideation of what is AI, feasibility to be used in BMS as an application, and what customers are using today. I think I touch based the topics that we spoke, case studies, how AI can optimize battery performance, battery health monitoring, and I think balancing I did not share. Um, um, and then challenge we are facing. Challenges, if I just take 1 minute, the everything is feasible only when it is cost effective. We can talk a lot about AI, but problem what happens, let's say you buy your bike paying 1.2 to 1.5 lakh. Any decent electric bike costs you about 1 to 1.5 lakh. Imagine every second you get about 60 parameters or 40 parameters in the data over the cloud. So every second. So imagine the amount of data that comes from each device, right? Somebody has to keep the data storage for all of this data that is coming from each vehicle. All of this need to be stored somewhere. You need to apply algorithms to run the models. So first of all, you need facilities to store data that is in the cloud. So it costs money. It is not free. And then on top of it, you need to run the algorithms on the back end, and you need to buy computational powers from cloud companies. It costs money. And then it doesn't stop there. Every day, every year, every month, there is activities going on in the cloud. So it is not feasible that easily without a lot of money. So when you buy a bike, you don't pay 1,000 rupees every month to manage your battery, right? And somebody has to spare that cost on the cloud and to do develop algorithms, to mature algorithms, and a lot of other things happens in the backend. So it's not just affordable, right? And you have IoT modules that's sitting on the vehicle. Each IoT module, every month, someone has to pay for that to send the data from hardware to the cloud. So that means every month you recharge your phone. The same way the automotive companies has to pay for the service providers of the SIMs to send data from vehicle to the cloud. So the cost effective feasibility is not easy for because you just pay about 1.5 lakhs, and we would expect the vehicle to be good for 7, 10, 20 years, right? So over 20 years, if you take it, it is so expensive for the OEM to just own this data, and that could be beneficial in many ways for them, but still the cost per vehicle is so expensive for them today to manage it. So maybe one fundamental limitation. There are a lot of other limitations because the cells keep changing, the chemistry keep changing over the number of years. They cannot just sit quiet and just doing one software. And that keeps changing every now and then, and that's the cost of developing, cost of maintaining, cost of running is a lot for a company today to develop solutions which just runs on AI. Maybe that's just a throw up on what challenges we are facing. Yeah, with that note, that's it from my side. We are left with another 5 minutes for Q&A. Any questions anybody have?
Sir,
Yes, sir.
one question in my side. Any possibilities to reduce the vehicle cost in futures?
So any possibility?
To reduce the vehicle cost in future, EV cost.
So a lot of today we depend upon China for parts, materials like battery. If you take 99% of the materials for the battery comes from China, the price depends upon the global market. The lithium price depends upon the global market. The material price depends upon the global market. So today we are in a very, very beginning stage of making batteries. Not even
Yes.
10 gigawatt of installed capacity that we have today. Even though we install, we buy everything from China still for the materials. So that means we depend upon X to reduce the price. So, but if you take globally, the battery prices are going down. That should impact the cost of the battery also. And then because that is a significant cost for the battery vehicle, so that may go down. That is one way of thinking. The other thing is that there are nowadays people are coming up with, you don't need to own the battery. You just own the vehicle without a battery. The battery is purchased on the lease basis. You pay per kilometer, something like that. So people may come up with these kind of an attractive financial options, and that's possibly the only way. And largely today we depend upon everything from external market, and whatever the cost happens in the global market, that also get dropped down to us, and that opens up a very less option that how much you can reduce in-house because you depend upon external resources for developing batteries.
Okay, sir.
Yes, sir. So there was one question about how often the window battery changes. I really don't know if I can give an answer. Just that uh, how I can quickly answer to that. But it depends upon an OEM. It depends upon really do they need to change something. Maybe a lot of other things, but I don't think so. I can maybe define how often that the thing changes quite quickly. All right, so I think then that's pretty much of the questions what we have for today. Ulpas, I think if that's all, so thanks a lot for providing the platform to share.
Any other question for participants? Okay, can we conclude, sir?
Yeah, madam.
Yes, ma'am.
We can conclude. I
So
think
we are deeply thankful to our distinguished expert, Mr. Suraj sir, for delivering insightful and technically rich session. Your explanation of battery management concepts combined with application of AI for state estimation and performance optimization has greatly enhanced our understanding of modern EV technologies. Your practical insights and real-time examples made the session highly informative and engaging. We truly appreciate your valuable time and effort in sharing your expertise with us. So we also sincerely thank to all the participants for their active involvement, meaningful interaction and enthusiastic participation, which added great value to the session. So thank you all. Thank you, sir.
thank you, madam. Thank you very much. I have shared my
Thank you,
email ID
sir.
in case. Thank you, sir. If in case somebody want to reach us for clarifications, you can reach me on that email ID. Thank you very much. Good night.
Thank you,
Good
sir.
night, sir.
Thank you very much. Thank you, dear participants. For today, day 2 sessions are over. Tomorrow, we are going to meet again at 6 p.m. for session number 5. Thank you. Thank you very much.
Thank you.